All right, good day, good morning. So for today, we'll be continuing, right, our plan, right, our flow chart from here. We've finished our discussion on variable separable, so now we will go forward with linear differential equations. So for linear differential equations, they require a bit more of a setup. Why is that the case? Because this method, right, another word or another name for this method is the integrating factor. This integrating factor is only going to work in very specific circumstances. What are those circumstances, you might ask? Well, this, right? The equation needs to first be arranged into something like this. And if you remember from earlier, our discussion, this is a linear differential equation, right? This is a first order linear differential equation. Why is that? Because you have here a y prime, you have here something that is attached to a y and something that is just a constant. No mixing of y's, no square root of y's, no y squareds, no y times y prime, nothing like that. That means that this is indeed, right, a linear differential equation, but what you need to do is you need to orient it like this. First, this dy over dx needs to be alone. Right? What do you mean alone? It has to be only multiplied to a 1. Say, for example, it's multiplied to a 3. What you need to do is divide everything by 3. Say, for example, it's multiplied by x squared. You need to divide everything by x squared. That's the first bit, right? Number 1, right? Isolated dy over dx. Next, number 2. What we will have in here is your px times y. What I like to do in this case is to recognize that this is the function by putting it in a box. And this is what we need to do. For number 2, I'm stressing this out because I'm emphasizing this because I made lots of mistakes like this before. This needs to be positive. So literally everything else that is not positive, right, you put inside the P, right? You put inside of this box, right? It's supposed to be, it should be plus px times y, right? Whatever is inside, whatever is beside that y value or that y variable, you should put it in the box. Say, for example, what you got was dy over dx minus xy equals x squared, something like this. What you need to do is basically put it inside the box, something like this, such that now it will look like dy over dx plus negative x times y is equal to x squared. Okay, that is what's supposed to be for number 2, right? Please put these things in a box, as well as number 3, right? The right hand side should not have y. That's it, right? Should not have y. For good measure, you might want to put it in another box, but that is now a little bit more unnecessary than earlier, right? Why is this the case? Because the way we're supposed to solve this is through this value of px. Whatever this function is very important because that is how we'll solve this thing, right? So the integrating factor if, right? The integrating factor if, to get that if, you will just have to do e raised to the integral of that px function, right? And in this case, what you don't need to do is we are used to putting in a plus c after we perform an indefinite integration, right? But in this case, I'm just looking for a function here. There is no need to write a plus c, right? So no need for plus c. So in this case, what we'll do, because it's called an integrating factor, is that you are supposed to multiply both sides by this integrating factor. Now you might say to yourself, well, I'm just making it harder for myself, right? What is so special about this integrating factor that it makes things easier or it makes things solvable? Well, I feel I should explain it better if we go and solve a problem by ourselves, right? So say, for example, this number 1, right? the thing about number 1 is that it actually is also variable separable. So you can check it if you would like, right? dy over dx, if I move it to the other side, this will become 2x minus xy. What you can do is pull out the x and then the 2 minus y, and then this is now variable separable. But I would like to solve this another way using this. Now now you guys can hopefully see that it is oriented the same way as our intended structure, right? The thing now, the only thing now that we need to do is just perform the boxing, because, well, that's very important. I will box out this x and this 2x as well, just so we understand that this x right here is the p of x and the 2x here is the q of x. Excuse me. Now, what will we do? Our integrating factor, because we've now put it this way, our integrating factor is now equal to, I feel like I should put that lower down. There you go. Our integrating factor is e raised to x dx. E raised to the integral of x dx, which is hopefully somewhat easy for you guys. It's going to be e raised to x squared divided by 2. That means that we're going to have to multiply both sides by e raised to x squared plus 2. And here's where things might be a little bit wild, more because, well, why am I doing this, right? Why am I making things more complicated, right? Shouldn't it be easier if we just didn't do this? But now, the magic of the integrating factor presents itself because of what's going to happen, right? X e raised to x squared divided by 2 times your y is equal to 2x times e raised to x squared over 2. Seems way more difficult, but now I will try and make things a little bit easier to spot. If this is your f, if you derive that, right? If you derive that, hopefully you can derive this in your brains, right? The derivative is this. So this is f prime. I'll put a plus in here. And say, for example, if I were to derive y with respect to x, because earlier we were deriving with respect to x, this would be your derivative, dy over dx. And so now you can see the whole of the left side is fg prime plus f prime g. Where have we heard of this before? We have heard of this before because this is the product rule. And the product rule that you are doing is basically you're deriving with respect to x this thing, right? F, right? Which is e raised to x squared divided by 2. That is your f, right? That is your f times your y, which is now your value of g, right? And now basically this is the state of our equation, right? We will have, oh, it's sunny again. We will now have this. And you might say to yourself, okay, maybe this is a bit more easy on the eyes, but still, look, from our original equation, that seems way more pleasing. But in this case, well, we don't need pleasing because this is solvable, right? And how do we solve this? The only way to solve this is through integrating both sides. So you might say, what, right? Well, what do you mean integrating both sides? We integrate with respect to x, right? So why do we do something like this, right? Why do we do something like this? Maybe I should move this a little bit to the side here, right? Why are we doing something like this? It's because, right, we are taking advantage of the fact that integration and differentiation are opposites. Much like if you add 3 then subtract 3, or if you multiply 3 and then divide by 3, nothing happens. The same thing will be true for differentiation and integration. If you derive this and then you integrate it back, you will just get the same thing. You'll just get the same thing, right? You'll just get this, which now removes, right? Which now removes the appearance of differentials. That is the goal of a differential equation in the first place, is to just remove the differentials, right? And now we will have something like this. The only thing left is for us to try and determine what this integral is going to be. And, well, good thing, because this is completely solvable as well. Say, for example, your u is x squared divided by 2. Your du will now be x times dx, which we have, right? So that means this whole thing is just going to be 2 times, right, du times e raised to u, right? So in essence, that will be 2 times e raised to u times du. And well, that is just going to be, let me write this down again. This will be equal to 2e raised to u plus c. And if we put back our u, that will be 2e raised to x squared over 2 plus c. Now, for us to get our final answer, we can just divide both sides by this e raised to x squared divided by 2, or we can just multiply both sides by e raised to negative x squared over 2. We will have our value, or our function y is equal to 2 plus c e raised to negative x squared over 2. This is our general solution, right? This is our general solution. Okay, that is our number 1. Now, let's try this out. I will no longer color code, right? No color coding any longer. And now, this is where the difficulty of the LDE, right? The linear differential equation, this is where the difficulty presents itself. In this case, it's not obvious at all that you should do a linear differential equation or that you should do an integrating factor. But in this case, well, you can try it out for yourself. Try and see if this is variable separable. You will see that it's not, right? And so now we can just try to arrange things. And plus, here is another bit of information. This does not only work for dy over dx. This works for every other flipped variable. What do I mean by flipped variable? What you can do is dx over dy plus py times x is equal to qy. You can flip those two variables. And why am I suggesting this? Because if you try it the original way, dy over dx, right? What you will do is you're going to have to divide dx on both sides. What you will have is this, right? Y minus x, I will move all of this to the other side. And then this is now equal to 1. And if you try to move it down, it becomes very difficult, right? Shall we say very difficult. However, on the other hand, what we will have is if we divide both sides by dy, right? If we divide both sides by dy, we will get dx, right? Dx over dy minus y, right? Plus x. Where is my plus x? Plus x is equal to 0. And now I am highlighting here the x's instead of the y's because the x is now the dependent variable. Or rather, we're treating it like one because it's the one on top. It's the one on the numerator of your differential. So now in here, we can try to, again, box different things. Okay, let's try this out and let's try to arrange it. The good thing here is that number 1, this dx over dy is already isolated, so there's no worries there, right? And then we can just move this to the other side. We will have our dx over dy plus x, right? What is beside the x? Well, it's just a 1. Is equal to just your value of y. Nothing much. Okay? And so now, right, the only thing left in here is to just try and get the integrating factor. But we have to remember again, right, what you might do for the integrating factor is you might just follow blindly that it is x. But in this case, this is actually a p of y, and this is a q of y. What we should do is we should integrate with respect to y. Py dy, which in this case is just 1, so e raised to the integral of dx, that is just going to be plain old and simple e raised to x. So now we will multiply e raised to x on both sides, and we will see, see, right? You see the issue, right? I'm saying you're blindly associating this, but then I'm writing it down myself, right? This should be e raised to y, and what will happen now is something like this: e raised to y times, right? Times dx over dy plus e raised to y times x is equal to y e raised to y. Now, again, we can see if this is your f, this is also your f prime. If this is your g, then this is your g prime. And we can say, aha, I see, you're just deriving with respect to y this time, this thing, e raised to y times x. And then now, we can equate that to this thing, y e raised to y. And what can basically happen while I'm putting these spaces is that we can just integrate with respect to y and integrate with respect to y. This and this cancels out. And basically, you will have just e raised to y times your x. And now this thing, if I remember properly, this is y e raised to y minus y. I will try this out now. Oh, no, it's e raised to y here. I'll try this out now. Y e raised to y is just e raised to y plus y e raised to y minus. Yeah, okay. So that is it. It just needs a little plus c at the end. And, of course, we need to divide everything by e raised to y, or just multiply everything by e raised to negative y. We will now have x is equal to y minus 1 plus c times e raised to negative y. And that is it. That is your general solution. Again, general solutions are present when we see a c, right? When we literally see any other variables that are, any other coefficients that are unsolved. And finally, now we come to the last example for our linear differential equation. X dy is equal to y plus ln of x dx. And in this case, you now have two possibilities as to what you're supposed to do. Number one, right? We're going to have to, well, try out dy over dx. And number two, we're going to have to try out dx over dy, right? What you can already spot here is that dx over dy is not possible. Why is it not possible? Because if you're going to treat your x as your independent variable, as your dependent variable, you will have here something that invalidates the linear differential equation, your ln of x. So we will have no choice but to just think about y as our dependent variable, which is indeed the default, right? This is going to be dy over dx, x times dy over dx. And then we move everything to the other side, right? We will have minus y minus, or let's just keep the ln x here, right? Okay. Now, we're still not done because this dy over dx still has an x beside it. So, we'll divide everything by x. And now we will get dy over dx minus, right? Minus 1 over x, right? Minus 1 over x. Let me get that a little bit farther away. Times y is equal to ln of x over x. You might be wondering, okay, what's wrong with this, right? Why am I putting so much space in here? It's because this is now negative. And so you might just say to yourself, aha, this is the thing that I'm going to use for the integrating factor. No, right? No. This is supposed to be positive, so you're supposed to put that negative sign in there. And then we can box this as well. This is our value of p of x. Therefore, this is what we will use for our integrating factor. Speaking of which, our integrating factor will be, right, e raised to the integral of px dx. That will be e raised to negative, right, negative 1 over x dx, and then that will be e raised to negative ln of x, right? And if you don't know what to do, because this looks complicated, I will remind everyone of the special relationship between logarithms and exponents. If you ever have an e raised to ln of something, what that does is that it will just return to you that something. If you have, on the other hand, an ln of e raised to something, it will return to you that same something. So in this case, the only thing that is bothering us now is that negative sign. But I will remind everyone again, a raised to m times n is just equal to a raised to m, and then you raise it to n. So in this case, this is what happens, right? What you can do is now you can split it as e raised to ln of x raised to negative 1, because that's the product of those two things. And e raised to ln of x, it's as if you're going to cancel out the e and the ln. You are going to be left with x raised to negative 1, which is 1 over x. That is our integrating factor, which means we can now apply that to both sides. We will have 1 over x times dy over dx minus 1 over x squared times y is equal to ln of x over x squared, right? Because you're also going to have to multiply it there. Now, again, right? This is f. That means that this thing is f prime. There's a plus in here, right? Because this is now negative, okay? And then if this is your y, if this is your g, then this is your g prime. Just like before, it's still a reverse of the product rule. So we should just do this, d over dx, and then this is going to be 1 over x times your y. And then that is going to be equal to ln of x over x squared. And the point now is that we should integrate and then integrate. Cancel, cancel. This will now be left as 1 over x times y is equal to, I don't know yet, right? We'll see. Let's try out here. The most common one would be ln of x. Let u is equal to ln of x, which means that your du is equal to dx over x. However, there is a problem. Excuse me. The problem here is that now you will have an extra x at the bottom. If you're going to separate these two, x, and then you can actually put this here, dx over x. What you can see is that only this will be, what do you call this? Only this will be counted as your du. What will happen to this x? Well, we can e raised to both sides, and what you'll get is that e and ln in here cancel. You will have x is equal to e raised to u. So now this can be transferred as u over e raised to u times du. You might say to yourself, okay, is this unsolvable? No, because what you can do is, now turn this e raised to u into u e raised to negative u du. And from there, we can do integration by parts. Maybe it would be better if we turned all of this into t, because we'll be using u dv and dv du, right? Those kinds of words. So let t is equal to ln x, therefore dt is dx over x, and x is equal to et. This is your dt, and this is your e, and your e raised to t, and then blah, blah, blah. T e raised to negative t times dt. Let's just choose this as our u, and everything else as our dv. That means that your u is your t, therefore your du is equal to dt. And then if your dv is equal to e raised to negative t dt, then that means that your v is equal to negative e raised to negative t. Right? And now we go uv minus vdu. Okay, let's try this out. uv is negative t e raised to negative t minus vdu, but because there's a negative in here already, I'll make that a positive, e raised to negative t dt, and that will just be equal to negative t e raised to negative t minus e raised to negative t plus c. And if you remember, right, our t is equal to ln of x, and your e raised to t is just x. So these things, this e raised to negative t, what you can do is just t over e raised to t, and then this is just 1 over e raised to t, and then plus c. Now, why is this important? Because we are going to turn this back into x. So now we will turn this back negative. Our t is ln x over x minus 1 over x plus c. And now we will have here on the other side 1 over x times y. So a great way to just cap this off would be to multiply everything by x. And we will have our general solution. Our general solution, which is negative ln x minus 1 plus c times x. Right? So you might say to yourself, wait, won't this negative 1 be removed? No. Right? This will not be removed because, well, it's no longer part of the c world because your c is now multiplied to an x, right? So those two are no longer together, shall we say, or they're no longer controlling the same bits. This is your value of y. Okay, so hopefully that was also a slight practice in integration by parts, right? This thing, integration by parts. So if you haven't, right, studied that in a while, please do study it, right? But yeah, that is it. And for next time, we will go on into exact equations, right? What the deal is with that one. So I hope you learned something from this, and thank you.